let's start the Monday seminar. So welcome everyone. So today we have Ryusuke Jinno. As many of you may know, he started a postdoc at IFT from November. And I think he will going to introduce himself. So please start.
Yeah, thank you very much for this opportunity. Actually, I started from October, if I remember correctly.
Sorry.
Yeah, thank you for this opportunity. So I'm Ryusuke Jinno, and today I will talk about first order phase transitions and gravitational waves in the early universe, with subtitle from Microphysics to Macrophysics. This title, I came up with this title to combine all these my works in a single phrase. Anyway, this talk is based on these works with people here. And I will first give you an introduction, and then I'll move on from the macrophysics side to the microphysics side about this first order phase transitions and gravitational wave production. And finally, I will summarize. So let me slowly start. So if I understand correctly, this is half self-introductory talk. So let me brief one slide overview about my career. So I got PhD in physics at the University of Tokyo in 2016. It's already 6 years ago. And I did postdoc at KK, Japan, and IBS in Korea, and DESY in Germany, and now I'm here in IFT CESIC. And today I'll talk about two specific topics, gravitational waves and first order phase transitions, but my research interests are not only limited to that. For example, this is a random list of my past works and future work. And for example, I'm interested in neural networks and soft collinear gauge production. I will talk about this today, actually. So please look forward to it. And also hydrogen neutrinos, Higgs inflation, unitary evaluation stuff, preheating stuff, or one dark matter small scale structures. All these are in my interest. And for example, post-Minkowskian black hole calculation using neural network integration comes, this kind of paper comes soon, or I'm also writing a paper about cosmic strings, and I'm working on formulation of tunneling problems. So I'm looking forward to work with you, with people at IFT. Yeah, so let me move on to the main part. Yeah, today's topic is these two. So let me first give you a very, very quick overview about first order phase transition and how first order phase transitions proceed in the early universe. Let's consider field space, and let's assume one thing. In field space, we assume that the scalar field of your theory has false vacuum and true vacuum separated by a barrier. And since our quantum field theory is quantum mechanics, essentially, so if the field starts from here, then it tunnels the true vacuum. And if you look at, if you invert the horizontal axis to the vertical axis, then in position space, the scalar field takes this kind of configuration when it tunnels. And this is called bubble. So let's move on to the position space picture. What happens in position space is bubble nucleation, expansion, and collision involving fluid dynamics. So let's take time axis in the horizontal direction. At some point in the history of the universe, small, tiny bubble nucleates. And then because the true vacuum is favored, they expand. And finally, they collide. And after this collision process, gravitational waves are produced following this wave equation. And even though I said that horizontal axis is time axis, this can be regarded as scale because all this phenomenon starts from very, very microphysics, your Lagrangian, your fundamental theory. And then the consequence of these dynamics is gravitational waves, which are produced by macrophysics size bubbles, cosmological size bubbles. So in this sense, first order phase transition is a very interesting topic, which requires understanding across all these scales. So let me go one by one, nucleation, expansion, collision. So the very microphysics side, you may ask, could it really happen? I mean, could the first order phase transition really happen? And unfortunately, within the standard model, the electroweak phase transition is crossover. But first order phase transitions occur in many extensions of the standard model. This is very incomplete list of extensions of the standard model, which allows first order phase transition. So the singlet extensions, 2HDM, N2HDM, and a bit more exotic is Randall-Sundrum extra dimension stuff, or confining transitions, or people sometimes consider very simple so-called classical conformal extension of the standard model. That's one motivation. And another motivation is, of course, first order phase transitions offer a possible explanation for the origin of baryon symmetry of the universe, also known as electroweak baryogenesis. So let's come back to this picture, microphysics to macrophysics. Now, let me explain the expansion stage. By the way, please stop me at any time if you have any question. Yeah, so this is the intermediate stage, bubble expansion. In a single phase, pressure versus friction determines the behavior of these expanding bubbles. So let me explain one by one. The first element is pressure. This comes from the released energy. As I wrote here, the potential difference is defined as raw vacuum. And when the raw vacuum is large, then the pressure from inward to outward is larger, of course. And if the potential is shallower, the pressure is weaker. So let's parameterize the pressure. Let's parameterize this raw vacuum by a dimensionless quantity, alpha, normalized by the plasma energy density. Here, plasma particles are everywhere in the universe. So yeah, so plasma, let's define this quantity. The second element is friction. Friction arises because, in general, this scalar field couples to plasma particles, and plasma particles push back the wall. So let's symbolically parameterize the coupling by eta. And in the next slide, I will show you how bubbles behave for different value of alpha. By the way, this expanding stage, intermediate stage, is, I would say, the most interesting because this kind of very microphysics, particle scale dynamics really, it's really connected to the macrophysics dynamics. I really like this intermediate stage. But anyway, let's see how bubbles behave for different alpha. So this is classification of bubble expansion. I took alpha in the horizontal axis and I classified into 4 classes, 1, 2, 3, 4, deflagration, detonation, strong detonation, and runaway. In the first 3 classes, the bubble wall reaches terminal velocity, the final velocity, because of the balance between pressure and friction, as I explained previously. And if this happens, the main energy carrier is the fluid profile here. But in contrast, if alpha is too large, the walls start to run away without caring about the plasma. And if this happens, the transition is like in vacuum. So the main energy carrier is the wall profile here. And yeah, let me show you the animation. The first, deflagration. The bubble expands like in this kind of self-similar profile. And what I plotted here is the temperature profile and fluid outward velocity profile. So for this kind of weak transition, the plasma particles in front of the wall is heated up, and also outward velocity arises in front of the wall. And bubble expands like this. Next, when I increase alpha slightly, the expansion mode slightly changes. The wall position is here, and you may notice the difference. The temperature is heated up behind the wall, and fluid outward velocity arises inside the bubble. So this is like bubble wall dragging the plasma particles. And when I further increase alpha beyond order 1, the profile again changes. Now the wall position is again here, but you see the temperature increase is very sharply localized around the wall position, and fluid velocity is also very sharply localized. And what I plotted in the right panel is the relativistic gamma factor of the fluid. So you see how energetic this fluid shell is. Now, finally, the wall starts to run away. If this happens, plasma particles cannot stop the acceleration of the walls. It means that the walls continue to accelerate until they collide with others. So let me stress that every detail of these bubbles contain the information of your microphysics, particle physics. Now let's finally review the collision part. So before explaining, let me show you one animation. And again, please stop me at any time if you have questions. In this animation, I took the weak or moderate function, this +1 or 2. And for this kind of weak transitions, bubble walls drive sound wave dynamics as shown in this animation. And this complicated sound wave dynamics produces gravitational waves. And if this happens, we have chances to detect gravitational waves. And sorry, I took this slide from my talk around 2017. So the figure is very, very old. But anyway, gravitational waves are defined as transverse traceless part of the metric. And if you take some gauge, then Hij gravitational waves live here. The deviation of the spatial component from Friedmann-Robertson numerical Walker metric. And if you expand the Einstein equation in linear order in Hij, then you get this kind of wave equation. The Landausian of Hij is Newtonian constant times some projection operator times energy momentum tensor. So this TKL, the energy momentum tensor, is the most important part. This is the source of the gravitational waves. And as we know, detection by LIGO and Virgo have been exciting us. And this is from detection around 2015, 2017. And these LIGO Virgo are so-called ground-based detectors. So let me introduce more future experiment. One of the best known is, of course, LISA, Laser Interferometer Space Antenna. It's a space interference project led by ESA and NASA. And I think experts are in this talk, I think. So I wouldn't say much about it, but LISA project is selected as third large class mission in 2017. And the important point is it's decided to be launched in 2034. And the basic configuration is like this. 3 spacecrafts orbiting around the sun. And the distance between these spacecrafts is only 10 to 6 kilometers. And if I remember correctly, people are testing necessary technologies with LISA Pathfinder since 2015. And the result was very successful. I heard it from some news. And this slide is summary of ongoing and future experiments, including LIGO, variable, and LISA. So there are basically 3 classes, I would say. The first one is grounding interferometers around 100 Hertz in the gravitational wave frequency. LIGO, variable, Kagura, Einstein telescope, all these ground interferometers are here. And another is pulsar timing arrays. These are around 10 to minus 8 Hertz. And the final category is space interferometers around millihertz to 1 Hertz. These are Taiji Tenchin, these are Chinese projects, and this I go Japan and DDO. I'm not sure about the current status of DDO. And the vertical, the vertical axis is, sorry, this is difficult to see. So definition of the vertical axis is the gravitational wave energy density rho GW for each logarithmic wave number, divided by, normalized by the total energy density of the universe. And if we are lucky now, the signal from bubbles come around this scale, if we are lucky now. So this is the last slide in the introduction. In the following, I will explain several of my works. And whenever I work on gravitational wave source of transitions, I have this in mind. What we need before the launch of space interferometers is to establish a reliable connection from particle physics to gravitational waves, from microphysics to macrophysics. That's my principle when I work on this topic. Now, let me explain some of my work. The first is about the macrophysics side. Let me start with some historical remarks. The traditional modeling. In calculating gravitational wave production from bubbles, the traditional modeling is so-called single and envelope. And an implicit assumption is no cosmic expansion during the transition. But the important assumptions are single and envelope. This is again animation, so let me show you. And the animation was a bit too fast, so let me stop here. And these two approximations, single and envelope, would be clear from this animation, I expect. Single means that the energy momentum tensor is localized in this very thin surface, infinitely thin surface. It means that Tij is 0, except for along the line. And another approximation, envelope, means that we take only this envelope, literally envelope, into account when calculating gravitational wave production. It's essentially the same as saying that the collided part of the wall dumps as soon as they collide. And also the energy momentum tensor along this surface grows as radius times normal vector Ni and J. And the reason, you may ask why this is proportional to radius. It's because the released energy is proportional to the volume of the bubble, radius cubic, divided by surface area, because all the released energy accumulates on the surface. So radius cubic, radius square gives radius linear. This is a traditional model. And the gravitational wave spectrum had long been calculated with this modeling with numerical simulations. Numerical simulation means that we generate this kind of bubble configurations numerically, and we track the surface and calculate the spectrum. And what I will explain from now is this system can be solvable analytically. following this paper. The derivation is very, very simple. It just needs consideration on causality, actually. So let me explain in 3 steps. The first step is to remind that the gravitational wave equation of motion is wave equation. The alarm velocity of h is essentially source Tij. So this equation can be solved formally with the green function. Convolution of the source with green function from -infinity to time t gives Hij t at time t. So in the schematic plot, there's some specific gravitational wave source integral when Tij is active. And we convolute Tij t prime times green function to get Hij at this time slice. The second thing is that gravitational wave spectrum, whatever spectrum, is 2-point correlator, 2-point ensemble average in cosmological sense. So it's Hij. And since we know that H is linearly related to T, so HH is essentially TT. TT means T some 4-dimensional argument, T some another 4-dimensional argument. This is easily calculable from the consideration of the causal cone of bubbles. This is one example of bubble configuration. And since Tij here and TKL here should be non-zero, otherwise this vanishes. So the bubble surface should pass through these x and y points. And here I couldn't plot the time component, but the time component is also implicit. And we can consider the probability for this kind of any configuration to happen, and we can calculate Tij TKL, and then we sum up over all possible configurations. So in animation, this is like this. We consider all possible configurations and calculate the probability and calculate the value of Tij TKL and sum up. This is one example, and another example is like this. You may notice the difference, but I will not explain. So the result, this is just for completeness. I will not explain anything, but the gravitational wave spectrum is contributed from the first animation in the previous slide and second animation in the previous slide. Yeah, I will not explain, but the result is simple exponential functions, spherical Bessel functions, and cosine, and that's it. And if you plot it, the gravitational wave spectrum becomes like this. This delta is proportional to omega, and it's peaked around the typical bubble size. This is very natural. Okay, sorry, this is just advertisement. This system was solved 24 years after the first proposal. And for example, the result is now used in nanograph people analysis. I took this from nanograph 12.5-year data set. And yeah, the model they're using is our result. And also this is review. This result is in review articles. And more precise analysis is also being performed. Okay, so but you may say, after all, modeling is just modeling. And the question is, does it really describe the real systems, right? I don't hear any feedback, but I hope you are listening. So one candidate that matches with the previous modeling is very strong transition, because the energy localization is very sharp. Can you hear me? I'm a bit worried that.
Yeah, I hear you.
Yes, very well.
Thank you. So one candidate that matches with this modeling is very strong transitions, because the energy is sharply localized like this. But several studies suggest that the shell remain alive even after collision. They don't die as soon as they collide. So we propose another modeling that takes this into account. Yeah, this kind of modeling. So let me again stop the animation. So the modeling is before collision, the energy momentum tensor grows in the same way as before, proportional to radius. But after collision, because any position inside this bubble, these bubbles, is in the true vacuum now. So there's no more additional energy release. So Tij decreases as 1 over surface area, so radius to the power of -2. We propose this kind of modeling and solve. So again, the gravitational wave spectrum is contribution from two distinct terms. And there are a few number of integrations like this, but basically they are spherical Bessel functions, cosine functions, and polynomials. And if you plot this, one interesting feature was found: IR enhancement of the spectrum. In this figure, the horizontal axis is the frequency of the gravitational waves again, and the vertical axis is the spectrum proportional to this omega. By the way, if you missed the definition of omega, let me remind you. Omega is here, the same omega in this. So let's come back. Previously, in the envelope approximation, symbol plus envelope approximation, the spectrum was like this. And this is a typical bubble size inverse. And once we take the long lifetime of the collided shells, the spectrum starts to behave like this. K to cubic changes to K to linear. Yeah, so that's this.
Ryusuke, how is the lifetime there?
Good question. The lifetime is determined by your microphysics. So unless you specify the microphysics, I cannot say specific. I cannot say lifetime is like this. I can say that. The maximal in maximally long-lived case, we know that the Tij is proportional to radius to the power of -2. But for example, if these bubbles are from scalar field, and if the scalar field decays into particles, then the lifetime might be shorter. So you need to specify the lifetime, the microphysics. That's the answer.
Okay.
And there are not yet many studies about this kind of lifetime. So it might be an interesting direction in the future. By the way, this is a little joke, but we called this modeling beyond envelope, but the name was not adopted by people in the field. And now they call it the bulk flow model, but whatever the name, that's, this is, yeah, whatever the name, physics is unchanged. So let's take a coffee break. 30 minutes or so.
You have 30 minutes.
So yeah, now we're at the half of the way, so that's a good pace. Another class of work about the macrophysics side is gravitational wave production from sound. And I showed these animations so many times, but please watch it again. In this animation, the bubble walls are on the bubble front before collision, but they're negligible in energy, as I briefly explained in this, when I explained this profile, expanding bubble profile. And these sound waves are driven by the bubble walls, and they work as a very efficient source of gravitational waves. And I haven't explained how I performed this 3D simulation. So let me very briefly sketch how this simulation works. We use so-called hybrid scheme. How does it work? In 3 steps. The step 1 is to generate nucleation points denoted by these stars in a box and create surface data like this. What does it mean, surface data? Surface data is the collision time distribution of each bubble in each direction. So for example, this theta and phi are angular variables for the bubble one. And depending on the direction and depending on other nucleation points, some surface element collides earlier and another surface element collides later. So in this way, we can construct the surface data for each bubble. And what's important is this surface data can be calculated without time evolution. Once we give these nucleation points, it's very easy and quick to calculate when each direction collides. Next, we already know the profile, fluid profile, before bubble collision, as I showed you in the animation of single expanding bubble. It's written by these blue lines. The left plot is enthalpy, the right plot is outward velocity. Enthalpy is roughly temperature to the fourth power, so it's essentially the same as temperature. And we already know this blue profile. And for the fluid profile after collision, we can simulate or we can approximate by 1D radial evolution. So the blue line evolves like this red line, and this is simulated in 1+1 dimensional simulation because it's 1D radial evolution alone. And by the way, this sharp discontinuity can be treated with some very smart scheme. So we clearly see that the sharp discontinuity remains even at late times. By the way, I'm very much interested in this kind of shockwave dynamics in the early universe. And if you want to discuss, please let me know. I'm very much interested in this. Not in the context of first order expansion, but in general, like large density perturbation, blah, blah, blah. Now, the final step, we embed this 1D evolution back into 3D lattice by rescaling for each direction, and then calculate the Gaussian waves. Once we embed into 3D box, we know the distribution of the energy moment of tensor, so we can just Fourier transform this distribution into the gravitational wave spectrum. This wave equation can be solved by Fourier transform. And this is one slice in the animation. We clearly see two different length scales. One is typical bubble size, and another is typical fluid shell thickness. So we expect that the gravitational wave spectrum has these two scales. And let me stress that these two scales are, again, determined by your microphysics. So this is very important information if we want to pin down your particle physics practice, for example. The wave number, gravitational wave spectrum. And we clearly see the typical bubble size inverse and typical fluid shell inverse. So we see, by the way, we see two different components, but this is a bit detailed, so I will not explain this today. And this is the last slide in the macrophysics section. I haven't explained why we need hybrid simulation. As you may notice, my hybrid simulation scheme is fluid-only simulation, but in real function, in the actual function, I don't know if it's in real or actual or, in real functions, we need the scalar field driving the transition. And how can this be justified? I mean, how is it justified that we simulate with only fluid? And rather, the motivation of this hybrid simulation is to remove the scalar field from the system completely. Let me explain 2 steps maybe, in real functions, the scalar wall is irrelevant to gravitational wave production in 2 double senses. One is that the walls are, first of all, negligible from the viewpoint of energy. I mentioned this before. The scalar wall is here or here, but as soon as the wall proceeds, it transfers almost all its energy to the fluid shell here or here. So the walls are negligible in energy, first of all. And another point is that walls have completely different length scale than others. Since the wall dynamics is determined from microphysics, if you consider TeV function or electroweak function, the wall thickness is, say, 1/100 GeV or 1 TeV. And this is much smaller than the fluid shell scale or bubble size. These two are cosmological size. Imagine the size of the present universe, for example. They're very, very different. So in these 2 senses, the walls are negligible in gravitational wave production in this kind of relatively weak functions. But if you perform simulations with the scalar field, these conditions are difficult to satisfy because it's in general very difficult to realize whatever hierarchy in 2 components in the simulation. So for example, the wall tend to have comparable scale with the fluid shell thickness, and the walls have order 0.1 fraction of the total budget of the system. So the walls tend to contaminate the result. So that's why we propose hybrid simulation, which simulates the system with fluid only. So that's the end of the macrophysics side. And let's gradually come back to the microphysics side. I will explain one paper, and I think I can explain this paper, but I can explain another paper too. So the first topic in the microphysics side is this bubble expansion stage. I showed you this picture previously. This is a cosmological scale bubble expanding, and if you zoom in the wall, what's going on is particle dynamics, particles impinging onto the wall, and sometimes they split. This determines all the fate of the bubble and all the gravitational wave signals. So let me state the question I would like to ask. How large is the friction from particles impinging onto the wall? Here, I take the wall to be very fast, almost speed of light. So let me draw a toy plot in the plasma flow. These blue dots are plasma particles thermalized with temperature T. And in very strong functions like this class 3 or class 4, the scalar wall hits these particles with this kind of incredibly large value of relativistic gamma factor. In some theories, gamma factor can be 10 to 10. This is crazy, but this is not theoretically excluded. So let's assume that the wall moves very, very fast. And this question determines the dynamics of the system and observables in extremely strong functions. And to make the discussion simpler, let's change the frame from the plasma frame to the rest frame of the wall. In the rest frame, the wall profile is very loose like this, but instead, these particles have extremely large energy enhanced by this relativistic gamma factor. And importantly, recently, people's understanding has changed very dramatically in 2017 for the case in which the transition involves gauge field. Before 2017, people thought that the main friction from these plasma particles comes from particles getting mass. Here, I explain why I wrote these particles with light blue and deep blue. Light blue is massless particle, and deep blue is massive particle. The particles get mass across the wall, so this back reacts to the wall, and it works. That works as friction to the wall. That was people's understanding until 2017. But from 2017, if the wall is moving fast, the story is completely different. The particle splitting process dominates. And here, this green line is gauge particle. So one particle splits into two, and this process dominates the friction, and it completely changes people's understanding. And since then, different results are reported from several groups. So let's define these particles. Let's give names to these particles. Particle A is the particle in the symmetric phase. I'm sorry, I inverted left and right compared to the previous plot. The incoming particle A is in the left, and it splits into B and C. The left is symmetric phase, and the right is Higgs phase, boson phase, or true vacuum, whatever the name is. I call it Higgs phase. Now let's name the particles B and C. C is the gauge particle. And what Bodecker and Moore pointed out in 2017 is, okay, let's consider this A to BC simplest process. This gives friction proportional to the wall gamma factor. The friction, this is force per unit area. So this is dimension 4 quantity. So this is dimension 4, mass times temperature cubic, dimension 4. And what they pointed out is this is proportional to gamma. And 3 years later, another group reported different or additional result. They say multiple splitting A to B CCC multiple C particle process gives even stronger friction, gamma squared. And if you remember the value of gamma 10 to 10 in the previous slide, you will understand that these two are completely different results, 10 to, let's say, 20 and 10 to 10. But later, Azatov and Van Flassela point out that this friction does not vanish in the transitionless limit. If the transition, if we remove the transition from the theory, then the scalar field value is 0. It means that mass of B particle, C particle, both are 0. So there should be no friction. That's their point. And this second result does not vanish in this way. And they pointed out that this is real. And in my paper at the end of last year, we discussed that A to B CCCC process rather is the same dependence as the original paper. So our results are more than a bit contradictory. So I hope I can convince you in the following. So let me explain. So first, let's parameterize. The particle, the energy of the particle incoming is EA. This is crazy large value, gamma factor enhanced. And it splits into two particles, and we have two parameters. One is X. X is the energy fraction carried by C particle. And we are interested in X around 0. So C particle is very low energy particle in the wall frame. And almost all the energy is carried by the B particle. And another parameter is K perpendicular. That's the momentum in the transverse direction. The B has K perp and C has minus K perp. And in reality, this is K perp vector, but to simplify the discussion, I wrote as just K perp. And we are interested in K perp around 0. Both are around 0. This is relevant. And we can write down the infinitesimal splitting probability in terms of the matrix element. And what is interesting about this kind of system, this kind of low-length violating system, is that the law explicitly breaks Z translation. Let's take this horizontal direction to be Z. The law explicitly breaks Z translation, and non-trivial matrix element arises from this violation of Z translation. So let's write down the matrix element. It's determined by the vertex function. For example, if you take scalar QED, then covariant derivative of your scalar field contains, for example, I shouldn't have written this as phi because this is confusing, but phi is the scalar part for A and B in this notation. If you expand this term, then you have this kind of momentum and polarization vector of the C gauge particle, and it can depend on Z because the background is Z dependent. But actually, this vertex function is not that important. What is important is this mode function of ABC particles. Usually, we have exponential IPA, Z, IPB, Z, IPCZ. And if you integrate over Z direction, we have this Z momentum conservation. That's this Z momentum conservation. But in the present case, since these mode functions are not simple exponential form, so once we integrate over dz, discontinuity or mismatch arises between the symmetric and broken case, and this gives non-trivial matrix element. And I omit all the steps to calculate this matrix element, but you can write down the mode function and you can integrate over. We get a single splitting probability, single splitting probability in terms of these two variables, x and k. And the result is like this: gauge coupling squared because the probability is matrix element squared, and we have this kind of logarithmically divergent structure, dx over x and dk pop squared over k pop squared times some non-trivial dependence. And our result goes to 0, where MC goes to 0. And by the way, here I introduced MCS and MCH, which means MC symmetric phase and MC Higgs phase. And you may ask, what is this symmetric phase mass? Because the particles are massless in the symmetric phase. And this is indeed a problem within our collaboration as well, and we haven't solved it completely. So let me explain. The soft collinear divergence is a problem, and that's why I, in the self-introduction, I said that I'm interested in soft collinear divergence, and I got interested from this calculation. So unless we have non-zero MCS or some other explicit logarithm for this K-pop argument, the result diverges actually. And there are several candidates for non-zero mu. Mu is defined as this. There are candidates for non-zero mu that kills the divergence. One is thermal mass. Any particle in the symmetry phase are thermalized. Particles are thermalized in the symmetry phase. So at least we have GT. Particles are thermalized.
Ryusuke, just to let you know, you have 10 minutes to PM.
Yeah, I think that's a very good case. So at least the C particle has gauge coupling times temperature. That's one argument. And the second argument is a bit complicated, so I will skip this. The third is non-portability. When X and K are too small, it means that the gauge particles are very IR. And if the gauge group is not U1, but let's say QCD, SU3, or more than that, then this kind of interaction term gets comparable to the kinetic term. So once this occurs, there's no clear picture about individual particle or perturbation theory calculation. So because of this kind of our ignorance about aerophysics, we can cut the integration at some value. That's the third argument. We took all these into account in our paper. And then, okay, that we calculated the probability for this single scraping. Then, what we found, well, this is as expected actually. The single scraping probability sometimes exceeds 1. And this is problematic because whenever we calculate probability, the result should be less than 1. But the result says, for example, 24, 38 like this in some cases. And what this signals is that we need resummation. What does it mean? Since this probability is large, it means that all these processes, all these diagrams beyond single scraping contribute to the real process. And it's well known as Stakov resummation. Once we take into account the leading law contribution of this kind of real emissions and also virtual corrections, then all these diagrams, or well, when you include virtual correction, not only matrix element, but anyway, all these diagrams organized in a nice way, and real emission is simply n emission, summation of n from 0 to infinity of n emission times some exponential suppression that comes from virtual correction. So the expectation value of our observable, the friction or momentum exchange, should be sandwiched by these two values. And this exponential kills the unjustified enhancement of the probability. There's clear interpretation about this. This is very, very close, the same as Poisson distribution. And the reason why we had probability 24, for example, is that we took only this lambda to the linear into account without taking care of this exponential. But once we sum all the leading law contributions, the distribution becomes Poisson distribution, and the entirety is automatically satisfied. So I will not explain the detail, but in our paper, we evaluated this Poisson distribution with semi-analytic way with various approximations and also numerical method. And one important point is, okay, let's calculate the friction. The friction comes from momentum exchange, momentum transfer from the particles to the wall. And what we want is average because there are so many particles. And there are two cases. One is these C particles reflected, and the other is C particle transmitted. And once we calculate these two contributions, they are comparable. So we have to take both into account. And for the Monte Carlo method, we follow very standard way, I think. X and K part variable in the horizontal and vertical axis. And we generated these towers of IR gauge bosons from uniform distribution in the logarithmic plane. And let me move to the conclusion, or results. So we calculate, so this is the result of our calculation, and sorry for this detail. This point is wall relativistic factor order 1, and here it becomes 10 to 5 or 10, or it increases with some power. And it's proportional, the horizontal axis actually is proportional to the transition strength alpha to the power of -1/4. And reflected contribution, transmitted contributions are plotted in blue and green lines. And the vertical axis is delta P normalized by some combination of parameters. And if this delta P is constant over across different scale, then friction is proportional to the gamma factor. Because this gamma factor arises from the phase space volume of the incoming factors. And if this instead increases like this, I hope you see the cursor. If it increases like this, delta P behaves as like, if delta P behaves like this, then the friction is not proportional to gamma. And what we found is that this is almost constant across this level of different scales. So we concluded that friction is proportional to gamma. And from this, okay, I have only 4 minutes, I think. So the wall, which is so from this result, we can determine whether the wall reaches the terminal velocity, as I showed in the animation, in the first 3 classes, or run away. The wall accelerates forever. I think forever actually, the wall accelerates. And this is the wall gamma factor when bubbles collide with a cosmological size. And finally, we can come back to the gravitational wave, the macrophysics consequences. As a function of transition strength and as a function of your transition scale, this is electronegativity scale, and this is, for example, Petrarchin scale. We can determine whether the gravitational waves are coming from sound waves, fluid dynamics, or scalar field dynamics. So let me summarize my talk. First order expansion and gravitational wave production are very interesting phenomena that require understanding physics across different scales. And before the launch of space interferometers like ISA, we have to establish the pipeline from microphysics side, particle physics, to the macrophysics side, gravitational waves. And many questions remain to be answered. So I'm looking forward to collaborate with you. Thank you very much.
Thank you, Ryusuke. Thank you very much for the nice talk. So we used up almost 1 hour, but if someone has question, please speak up or you can raise hand.
If you don't have any questions, I have four additional topics. If you want. I have 2 PH related topics, and I have more.
No, we use up 1 hour. But I have a question if nobody.
I will stop.
Yeah. So about this the last particle splitting, it gives time dependent friction, right? So the picture of bubble collision change depending on the time of from beginning to end of phase transition, that it changes the friction, right? And I guess my question is how does it affect gravitational wave? You briefly.
Yeah, I have answer. So let's look at typical bubble expansion because okay, even though this is relatively deep function, but the bubble size itself is not that different between two cases. So let's look at this. We have typical bubble size. So for example, we have, for example, large bubble here and small bubble, let's say here, 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 and there. But they're not, let's say, they're not different by, let's say, 10 to 3, by factor of 10 to 3. They're at most different by 10 or maximum 100 or something like that. And from the viewpoint of gravitational wave production, what dominates the gravitational wave production is big bubbles. So yeah, in principle, you're right, because the friction is time dependent, or more precisely, the radius dependent, because small bubbles has not accelerated much, so the friction is smaller if the friction is proportional to gamma factor. The big bubble has more friction. So the friction, in that sense, changes might appear, but from the viewpoint of typicality, we can discuss the friction for the typical big bubble. So the result will not be that different.
I see. I see. Thank you. Is there other question?
If you could say a little more about the back reaction, you mentioned that it's tough to include back reaction effects at some point. If you could say just a little bit.
Yeah, little bit. So
yes,
I listed this back reaction in the single splitting slide, but this is actually about the multiple splitting. This is about multiple splitting, so that's why I skipped it. So each C particle emitted has at least energy MCH once they enter inside the bubble. So if we assume that, so first, soft collinear divergence means that this kind of higher gauge bosons are produced infinitely many in number. But if these gauge bosons all enter the bubble, then they all have MCH energy at least. So their energy diverges. And it's not allowed. So because each emitted C particle has minimum non-zero energy, so there's no probability, no possibility for infinitely many C particles to be produced. That's the second thing.
I see.
Does it answer? Or, yeah, I think this is confusing. I shouldn't put this the single statement.
But now I get your point, though. Thank you.
Any other question? Then, if not, let's thank Ryusuke again. Thank you very much.
Thank you.
We close the.
Thank you.
So, Kuranagi-san, can you stop the recording?
Yeah, sure.